There is a moment, somewhere between the last confirmed radar sweep and the silence that follows, when an aircraft stops being an aircraft and becomes something else entirely. It becomes a question, a wound, a hole in the logic of the world. And for the people left behind, the families checking flight boards, the air traffic controllers staring at empty screens, the naval officers tasked with finding something that no longer wants to be found, the hardest part isn't the loss, it's the not knowing. The geometry of grief changes completely when there is no wreckage, no crater, no obvious ending. The mind can't build a wall around a space that hasn't been defined. This is a story about that space, about a patch of ocean where the seabed stayed quiet for years, unremarkable, unvisited, undisturbed, and about a single stubborn signal that refused to let the world forget what had fallen there. To understand how an aircraft vanishes in the 21st century, you have to first understand something counterintuitive about the ocean. We often think of the sea as a flat thing, a surface. We watch it from beaches. We see it from planes. We know it as a color on maps, that even, calming blue. But the ocean is not flat. The ocean is deep. It is layered. It is a vertical wilderness that makes the Himalayas look like a rumor. Below the surface, the physics change. Light is gone within the first 200 meters. Temperature plummets through the thermocline, that invisible boundary where warm surface water meets the colder abyss beneath it. Pressure builds at a rate of roughly 1 atmosphere for every 10 meters of descent. At 3,000 meters, roughly the average depth of the world's oceans, you are dealing with 300 times the pressure of the air you are breathing right now. Metal warps, seals fail. The engineering that kept an aircraft in the sky means nothing to the engineering required to find it at the bottom of the sea. And yet, it is sound, not light, not pressure, not depth, that becomes the protagonist of this story. Because the ocean, despite its silence to human ears, is not silent at all. It is one of the most extraordinary acoustic environments on Earth. In 1943, during the height of the Second World War, a pair of physicists, Maurice Ewing and J. Lamar Worzel, discovered something remarkable. At a certain depth in the ocean, somewhere between roughly 600 and 1,200 meters, there exists a layer where the speed of sound reaches its minimum. Above this layer, sound speeds up because the water is warmer. Below it, sound also speeds up because the water, though colder, is under such immense pressure that the pressure effect outweighs the temperature effect. The result is a natural acoustic channel, a horizontal corridor in the water column where sound waves become trapped, bouncing endlessly between the faster layers above and below, losing almost no energy as they travel. They called it the SOFAR channel, sound fixing and ranging. In good conditions, a sound generated in the SOFAR channel can travel thousands of miles. During the Cold War, the United States Navy laid networks of hydrophones along the ocean floor specifically to listen for Soviet submarines exploiting this phenomenon. Whales use it to communicate across entire ocean basins. A low-frequency call from a blue whale off the coast of Antarctica has been detected by hydrophones near Bermuda. The ocean remembers sound far longer than it remembers anything else. And this detail, this quiet, beautiful fact of physics, turns out to be everything when you are searching for a missing aircraft. Because when a modern commercial aircraft crashes into the sea, it carries with it a small cylindrical device, usually no bigger than a flashlight, bolted to its flight data recorder and cockpit voice recorder. This device is called an underwater locator beacon, and it does only one thing. It waits. The moment salt water touches its sensor, a spring-loaded mechanism activates a lithium battery, and the beacon begins emitting an acoustic pulse at 37.5 kilohertz, once every second without interruption for a minimum of 30 days. Newer models, mandated after the loss of Air France Flight 447 in 2009, operate for 90 days. The pulse is not loud. It is not dramatic. Under ideal conditions, it can be detected from perhaps 2 kilometers away, and in deep, noisy water, often far less. The aviation industry calls this device a pinger. The word itself is almost dismissive, clinical, small, a verb turned noun. And yet, in the aftermath of an ocean crash, this pinger becomes the most important object on Earth. It is the voice of the dead, the one sound the seabed makes that means something human. Now, imagine the following scenario. An aircraft disappears. Radar contact is lost over open ocean. Within hours, the world learns of the disappearance. Search aircraft are scrambled, ships are diverted, satellites are retasked. The initial search, as always, focuses on the surface, looking for debris, oil slicks, floating seat cushions, personal belongings, anything that the ocean hasn't yet swallowed. But the ocean is fast. Surface currents can scatter a debris field across hundreds of square miles within days. Wind and wave action break apart what little flotsam reaches the surface. And in many cases, particularly when the point of impact is uncertain, the surface search reveals nothing at all. The sea offers no comment. Attention then turns to the deep, to the acoustic search. A ship towing a hydrophone array, a device called a towed pinger locator, begins sailing a painstaking grid pattern over the probable impact area. The hydrophone hangs deep, sometimes thousands of meters below the ship, listening. The operators wear headphones and stare at spectral displays, watching for the telltale signature, a sharp, narrow spike at 37.5 kHz, repeating once per second. In the vast quiet of the deep ocean, that signal, if it exists, is unmistakable. But here is the problem. The probable impact area might be enormous. In the case of Malaysia Airlines Flight 370, which vanished on March 8, 2014, the initial search zone covered tens of thousands of square kilometers of the southern Indian Ocean. The water there reaches depths of 4,000 to 6,000 meters. A towed pinger locator moves at roughly 1 to 2 knots. At those speeds, covering even a modest search box can take weeks, and the pinger has a deadline, 30 days. 90 if you're fortunate. After that, the battery dies, and the ocean swallows the sound, along with everything else. But what happens when a signal is detected, not during the frantic window of the pinger's life, but later, much later? What happens when the seabed, after years of silence, produces a sound that shouldn't exist? This is where the story changes register, where it stops being a procedural account of search technology and becomes something stranger, more unsettling, and far more interesting. Because signals have been detected in the deep ocean that cannot be easily explained. Acoustic anomalies picked up by hydrophone networks, spikes at frequencies suspiciously close to 37.5 kHz in areas that overlap with the predicted resting sites of aircraft that were never found. Not pingers. Not exactly. The batteries would be long dead, but something. The scientific explanations are varied, and each carries its own weight. Some researchers have proposed that the metallic wreckage of an aircraft, settling and shifting on the seabed over time, can produce faint acoustic emissions. The sound of steel slowly yielding to pressure, of fuselage sections collapsing inward under the weight of thousands of meters of water. These sounds are low energy, intermittent, and easily lost in the ambient noise of the ocean, but they exist. Others have pointed to a phenomenon known as bioacoustic colonization. When a large object, a shipwreck, a boulder, an aircraft fuselage, comes to rest on the ocean floor, it becomes, over time, an artificial reef. Marine organisms colonize its surfaces. Crustaceans click. Fish drum. Certain species of shrimp produce sounds in the ultrasonic range that can, under specific conditions, approximate the frequency of an underwater locator beacon. Not perfectly, but close enough to confuse a hydrophone operator listening for something they desperately want to hear. And then there is the most haunting explanation of all: the geological one. The ocean floor is not inert. It breathes. Tectonic plates shift. Sediment layers compress and release gas. Hydrothermal vents exhale columns of superheated fluid. And in certain regions, particularly along mid-ocean ridges and subduction zones, the seabed produces its own acoustic signatures. Low groans, high-pitched clicks, rhythmic pulses. These are the sounds of a planet still forming, still cooling, still settling into itself. And occasionally, by pure coincidence, these sounds occur at frequencies that echo the very signals search teams were sent to find. The ocean, it turns out, is capable of mimicking the dead. Consider the case of Air France Flight 447. On June 1, 2009, the Airbus A330-200, carrying 228 people from Rio de Janeiro to Paris, crashed into the equatorial Atlantic Ocean. The surface debris was found within days, but the aircraft itself and its black boxes lay hidden on the seabed for nearly 2 years, at a depth of roughly 3,900 meters. During those 2 years, repeated acoustic and sonar searches failed. The pinger batteries had long expired. The ocean floor in that region was a labyrinth of underwater ridges, volcanic terrain, and deep valleys that scattered sonar signals and created false returns. The seabed, in effect, was actively working against the search effort, not through any malice, but through the sheer complexity of its topography. It was not until the Bureau of Enquiry and Analysis, the BEA, France's Civil Aviation Safety Investigation Authority, commissioned a reanalysis using Bayesian probability modeling and high-resolution autonomous underwater vehicles, specifically the Remus 6000, that the wreckage was located. The AUVs carried side-scan sonar systems capable of producing near-photographic images of the sea floor. They flew just a few dozen meters above the bottom, capturing detail that ship-mounted systems could never achieve. And when the wreckage was found, it was not dramatic, it was quiet. A field of debris scattered across a rocky plain. Engines half buried in sediment. Sections of fuselage recognizable only by their curvature. The cockpit voice recorder and flight data recorder were recovered intact, their data preserved despite 2 years of immersion in salt water at crushing pressure. The black boxes told the story. Pilot error in response to a failure of the airspeed indicators. A stall at high altitude. A descent that lasted 3.5 minutes. The ocean had held the answer the entire time, waiting for someone to ask the right question in the right way. But Flight 447, as agonizing as its search was, had a crucial advantage. A known crash location within a relatively bounded area. The real nightmare, the scenario that haunts search coordinators and acoustic engineers alike, is when the impact point is uncertain. When the last radar contact provides only a vague heading. When satellite data must be reverse engineered from handshake logs, never designed for navigation. When the probable search zone isn't a grid square, but an arc stretching across thousands of miles of open ocean. This is the territory of the stubborn signal. Because when the initial search fails, when the pingers die, the surface yields nothing, and the sonar sweeps come back empty, the case doesn't truly close. It can't. There are families. There are regulatory bodies. There are insurance claims and international obligations. And there is the simple, unshakable fact that somewhere on the floor of the ocean, an aircraft is sitting in the dark, and nobody knows exactly where. And so the listening continues, not with dedicated search vessels necessarily, but through the vast, quiet network of hydrophones that have been anchored to the ocean floor since the Cold War. The Comprehensive Nuclear Test Ban Treaty Organization maintains a global network of 11 hydroacoustic stations designed to detect clandestine nuclear detonations. These stations listen continuously, recording everything: whale calls, earthquakes, volcanic eruptions, iceberg calving events, ship propellers, and sometimes anomalies, sounds that don't fit neatly into any category. It is through this network that stubborn signals occasionally surface: an unexpected pulse at the right frequency, a pattern that repeats with suspicious regularity, a sound that, when cross-referenced with the predicted drift models, the satellite geometry, and the ocean current data, points to a patch of seabed that no one has yet examined. These signals are never conclusive. They are always ambiguous. They sit in the uncomfortable space between evidence and noise, between hope and pareidolia, the human tendency to find patterns in randomness. And yet they persist. They are logged, analyzed, debated at conferences, and filed in databases that grow thicker with every passing year. One such signal, faint, irregular, but stubbornly present at intervals that defy easy explanation, was reportedly recorded by a hydroacoustic station in the Indian Ocean in the years following MH370's disappearance. Researchers at Cardiff University and Curtin University analyzed the data. They found low-frequency acoustic events consistent with the timing of the crash. The signal had traveled thousands of kilometers through the SOFAR channel, arriving at the hydrophone array, distorted but intact. A whisper carried halfway across the ocean by the physics of deep water. Was it the plane? Was it the impact? Was it the sound of 239 lives ending at the surface of the sea? The researchers were careful. The data was suggestive, not definitive. The signal was consistent with multiple possible sources, but it was there, it was real, and it refused to be ignored. This is the fundamental tension at the heart of every underwater search for a missing aircraft. The technology is extraordinary. Autonomous underwater vehicles can now map the seabed with centimeter-level resolution. Synthetic aperture sonar can distinguish a soda can from a rock at a distance of 200 meters. Machine learning algorithms can process thousands of hours of acoustic data in minutes, flagging anomalies that would take a human operator weeks to identify. And yet, the ocean remains, in the most literal sense, unfathomable. We have mapped more of the surface of Mars than we have of our own ocean floor. The abyssal plains, those vast, flat expanses of sediment that cover the majority of the deep seabed, are among the least explored environments on Earth. A Boeing 777, which is 64 meters long and has a wingspan of 61 meters, would be an insignificant speck on the floor of the Indian Ocean. It would be a needle in a haystack the size of a continent, buried under a blanket of water 4 kilometers thick. The search is not a failure of technology. It is a confrontation with scale. And so the stubborn signal endures. It sits in the data like a splinter. It keeps researchers awake. It draws funding proposals that are written, submitted, rejected, revised, and submitted again. It fuels new expeditions, like those conducted by Ocean Infinity, a marine robotics company that has now spent years and millions of dollars deploying fleets of autonomous underwater vehicles across the southern Indian Ocean, scanning the seabed in systematic passes, searching for the one acoustic return, the one shadow on the sonar display that would end the longest and most expensive search in aviation history. Ocean Infinity's most recent campaign concluded in early 2026, having mapped more than 140,000 square kilometers of seafloor, an area larger than England, without finding the aircraft. The search was conducted on a no-find, no-fee basis. They found nothing, they were paid nothing, and still, they have spoken publicly about returning. Why? Because the signal is still there. Because the data still points to the ocean floor. Because the absence of evidence, in this case, is not evidence of absence. Because the aircraft did not evaporate. It did not ascend into another dimension. It went into the water, and the water kept it. And the water is telling us something, if only we could listen with enough precision. There is a term in signal processing called the noise floor. It refers to the baseline level of background noise in any detection system. The static, the hiss, the ambient rumble that exists even when no signal is being transmitted. Every sensor, every hydrophone, every receiver has a noise floor, and any signal you hope to detect must rise above it. The ocean has its own noise floor. It is composed of wind-driven waves, distant shipping traffic, marine life, seismic activity, and the thermal motion of water molecules themselves. It is constant, pervasive, and deceptively complex. And somewhere within that noise, buried, distorted, barely distinguishable from the background, there may be a signal, a pulse, a reflection, a stubborn acoustic fingerprint left by an aircraft that the world has been searching for. The question is not whether the signal exists. The question is whether we have the tools and the patience to extract it. And that patience is not an abstract thing. It is measured in the faces of families who have waited years without answers. In the engineers who have spent careers building sensors capable of detecting fainter and fainter sounds. In the investigators who have refused to close cases that remain technically and morally open. Patience, in this context, is not passive. It is a form of defiance, a refusal to accept that the ocean's silence is the final word. The seabed is quiet. It has been quiet for years. But quietness is not emptiness. Beneath the sediment, beneath the layers of biological detritus and volcanic dust, there is wreckage. There is metal. There are flight recorders whose data, even now, may be recoverable. There is an answer to a question that has haunted hundreds of families and an entire industry. And there is that stubborn signal, faint, ambiguous, maddeningly persistent, rising from the noise floor like a hand from dark water. It doesn't say much. It doesn't need to. It says only this: I am here. I have always been here. Come find me. The ocean keeps its secrets, but it doesn't keep them forever. It holds them until the technology catches up, until the algorithms become sharp enough, until someone builds a sensor sensitive enough to hear what the deep has been trying to say. That day may be closer than we think. It may already be here. And when it comes, when the sonar finally resolves that one shadow into a shape, when the acoustic anomaly is finally traced to a set of coordinates, when a remotely operated vehicle descends through 4 kilometers of darkness and its floodlights illuminate the unmistakable silhouette of a fuselage on the ocean floor, the silence will break. Not with a roar, not with fanfare, but with a quiet, definitive click. The same sound the pinger made, once per second, for 90 days, in the darkness, in the cold, in the crushing weight of water, speaking to no one and everyone at the same time. I am here. I am here. I am here. The search continues.